Good morning. It's so good to see y'all, all y'all. I wish you could see each other. I so wish you could see each other. We're getting closer. I think we'll be on face to face in the fall. There's just such good news about vaccinations. I think we're going to do this. So, anyways, that will be wonderful. All right. Let's see. We are going to finish up that last problem on the worksheets, and then we're going to do 3.6b and 4.1. You have spring break all of next week. Yay! Enjoy the spring. Enjoy hours, spring being pushed forward, that hour that we lose on Sunday. And then we'll get back here the week after that on the 22nd, I think we meet. We do these 3 sections, and then we will review for the test on Monday of week 10, and your deadline will be April 2nd. I'm going to scoot everything back to April 2nd. My math lab will be due April 1st. I haven't changed that, but I will. I will change that. Between now and sometime this afternoon, I will open up all of my math lab. So the 5 of you that don't have A's on my math lab ought to think about spending some time getting your grade up. It's points that you can earn on your own. It's just points that are there for the taking. And those of you who have A's but not 100 might think about going in there and cleaning up some of that. You do you. Okay, let's look at that last one we were doing. Let's go through these just real briefly. Here's my little list of what we're doing. Let's move this up a little bit. Let's see if we can get a better idea of what's going on here. Okay, so the first thing we're doing is vertical asymptotes. That amounts to setting the denominator equal to 0. So x equals 0. That's our vertical asymptote, and I drew it in there. Horizontal asymptote, that's the 3 rules. Let's look at those 3 rules. Horizontal asymptotes, let's see, what do we have? We have a top heavy. If the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote, so no horizontal asymptote there. Third thing, x-intercepts, you're setting the numerator equal to 0. That's the difference of 2 squares, so we're getting x equals 2 and x equals -2. That means we're going to go through those points. Our boomerangs will go through those 2 points. Y-intercept, do f of 0. You get 0 minus 4, so you get a -4 over, you've got a 0 in the bottom. So we have none. And we know that. We know we're not going to have a y-intercept because we can't get onto the y line. Okay, that brings us up to slant asymptote. One thing that we did not cover because this is the only problem that covers it. So slant asymptote, let's look. A rational function will have a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. So it will be top heavy, where we said there was no horizontal asymptote. So there won't be a horizontal line going through, but when it's 1 degree, like x to the 3rd over x squared or x to the 4th over x to the 3rd, we're going to have a slant asymptote. We're going to have a slanted line, one way or the other, about which our function cannot cross, or through which our function cannot cross. To find an equation of a slant asymptote, divide the numerator by the denominator using synthetic division. The slant asymptote will be in the form y equals what we got for our answer. So I know that's a lot of words. Let's do 1 so I can show you what it's going to look like. In this particular problem, to do the slant asymptote, we're going to be dividing x squared minus 4 by x. Now remember, we didn't ever have an x to divide by. If we had had an x minus 3, we'd be dividing by 3. If we had an x plus 2, we'd be dividing by -2. You use the opposite of what sits there. Same thing here. What sits out there is a 0. So we're going to be dividing by 0, which is a little bit strange. And we're going to divide it into x squared minus 4. So using the coefficients in front, x squared has a 1. We need an x term, that's a 0, and then that -4. And then synthetic division, 1 times 0 is 0, 0 times 0 is 0, we get a -4. That's a remainder, we don't care about that. We're looking for this to tell us what the slant asymptote is. This was x squared. That means this is x. So it will be in the form of y equals what this says. This says to us x, 1x, and no number. So there's our slant asymptote, y equals x. That asymptote goes as a 45-degree angle, doing dot, dot, dots through there. So there's a horizontal a slant asymptote. That's a slanted line. So we're going to have to stay in this corner and this corner. We won't have anything in the other two. So let's see where those are happening. And that's what we're going to do about the fifth one, additional points. Make sure this is on the screen. Yeah, it is. Okay, so we know what's happening when x is -2. Let's see what's happening when x is -5. Remembering these are boomerangs, so we're looking, we know what shape it's going to look like. Put a -5 in there, and we'll get 25. Having some troubles with my pen. 25 minus 4 over 5. That's 21 over 5, which is about 4, a little bit more than 4. So -5, +4. Oh, that was a -5. Okay. Negative, I blew it here. It's a 25 minus 4 over x. So that's a -5, that's a -5, and that's a -4 in a little bit. So -5, -4. So we're going to go right to here. 1, 2, 3, 4, and a little bit. Okay. So that's telling me this is going to boomerang like this. If you want to check it, we can check a -1. So let's put in a -1 and see that it doesn't happen up here. So -1 squared is 1. 1 minus 4 will give us -3. -3 over -1 will give us a 3. So this point is -1, +3 right there. And yeah, you can see that boomerang happening. Something like that. It's going to sidle, let me get rid of this out of here. It's going to sidle along here. This asymptote, or sorry, this arm of the boomerang will get closer and closer to this 45-degree angle slant asymptote, but never quite reach it, never cross it. This arm will go up here towards positive infinity on the y-axis as the x arm gets closer and closer to that asymptote of 0. Okay, we know this is going to be symmetrical, but let's just check it. I mean, you don't know that necessarily, do you? So let's look, let's take the point 1. That's an easy number to take. 1 squared minus 4 over 1. That's -3 over 1. So we get 1, -3. 1, -3 like that. So it's sidling up against this asymptote, and we would expect the other to do that. So let's just draw that in. That sort of thing. Okay, let's finish this up. Number 6 is looking at, our last thing we were looking at was symmetry. This does not have y-axis symmetry. We don't have the same thing over here that we have over here. I mean, this guy is way up higher than this one. So we don't have that, but let's check and see if we don't have origin symmetry. If we put a -x in there, -x squared will give us x squared. -4 won't change. X will turn into -x. We can then take that negative and put it out in front, which gives us, hang on, which gives us this original piece, what we started with a minus sign in front. So that tells us if our original function has a negative, then we've got origin symmetry. And sure enough, if we were to take our little drawing and spin them around 180 degrees, this arm would become that arm. This arm would be down here doing that. So this is our only one that we had any symmetry on, in case you were wondering. Okay, let's do a couple of those as x's. As x becomes 0 from the positive side. Let's look at what happens as f of x, what f of x approaches. So as x is approaching 0 from the positive side, okay, we've got 4 hands here. We've got 2 sets of arms, 4 things are happening. They're asking us about one of them. So let's first figure out which one they're asking us about. We're looking at as x approaches 0 from the positive direction. So we're coming from the right, going this way, approaching 0. Well, we've already passed this arm. This arm is not approaching 0 on the x. He's going out that way. So we're talking about this arm right here, as this hand is approaching x on the 0. So as these numbers, this was a 2 on the x, this was a 1 on the x, this is getting closer and closer to 0 from the positive side, they're asking you what's happening on the thermometer. F of x, that's y. What's happening on the y? What on these points? This is this point right here is 2, 0. This point right here is 1, -3. Good, perfect, Chloe. This guy is going down here further and further and further. So as the x is getting closer to 0, the y is tubing, going to -infinity. Okay, let's do one more of those. As x approaches 0 from the negative direction, again, they're always asking you what y is doing. You just got to figure out which hand they're talking about. So as x approaches 0 from the negative direction, so come from over this direction, from -6, -5, and look and see where x, it's going to have to be one of these 2 hands because we can't cross this wall. So if we're going, as we're approaching 0 from the negative, this guy's not approaching 0. He's going out that way. He's going back that direction. So we're not talking about that hand. As x approaches as x approaches 0 from the negative direction. So we're talking about this arm and asking what its y is doing. And its y is flying up that way toward positive infinity. So we're always talking about one of the arms. Okay, we're done with that. Let's look at 3.6b. Oh, I noticed so many of you got in and got all those 3.6a's done. So this will make a lot more sense to you, which thrills me. Things making sense is what we want here. Okay, so let's look at x plus 6 over x plus 7 is less than 0. We've got 2 different things going on. We're going to be looking at the number line just like we were before. Let's set each of these, even though this makes a ratio, rational inequalities, there's a ratio going on in there, and we've got an inequality. Even though they're not next to each other, we're still going to look for goalposts based on setting them equal to 0. So x is -6 and x is -7. Put those on a number line, and then it says less than. So what we're going to do is the same thing we were doing before. Less than means go in between. So our answer here is the inside. Remember, just like on 3.6a, less than means shade the inside piece between the 2. Greater than means shade the outsides. Okay, we don't have our equal to's here, so we're shading, we're putting not including. And we've got -7 to -6 with parentheses. Super easy, no weird stuff happening. Got a lot of weird stuff that's going to happen in the next 1, 2, 3, 4, 5 problems, but nothing unusual there, nothing different from what we did on Monday. That's the first one. Let's look at the second one. -x plus 4 over x minus 10 is greater than or equal to 0. Okay, there are 2 weird things that are going to happen here. We have a -x with an inequality, so that's going to throw what we do over here. And we've got an equal to possible here saying, let's move forward. Let's go ahead and put them equal to 0. Same old, same old. X minus 10 equals 0, so x equals 10. I'm going to move the x over here so it's a little easier to see. It's just one step. X equals 4. So we have a 4 and we have a 10. And it says to shade the outside, But that's not always going to work because we've got a negative x, and that's going to throw some stuff. So what we want to do instead is we want to check it. We're going to have to check it. You're going to have to grab a point from one of the segments, one of the intervals. It doesn't matter where. You just have to keep track of what you're looking at. So I think I'm just going to grab the number 5. 5 sits in there. That's going to be my check. I'm going to check 5. You can pick any number you want. It doesn't have to be from this segment. It can be from anywhere. You could pick 0 if you want to. I just decided on 5. So my check of 5 is -5 plus 4 over 5 minus 10. It's got to be greater than or equal to 0. So I get a -1 over -5 has got to be greater than or equal to 0. So I get a positive 1/5. And positive 1/5, that's a positive number, really only matters if it's positive or negative, is greater than or equal to 0. Yeah, that is right. So my checked number worked. That means he's part of the answer along with all of his little buddies there in the interval between 4 and 10. So that's the first trick. When you've got a negative x, you can't just go with this sign. You got to be careful on it. You're going to have to check when you've got a negative. So watch out for that first whenever you've got a negative x in your problem. The other thing is this or equal to. If we make 4, if we include 4, and we're going to, I'm going to put a bracket there. -4 plus 4 is 0, and 0 on top is not a problem. 0 will be equal to 0, and that's cool, no problem. It is a problem, though, in the denominator, so that's another trick area. What if you put a 10 in there? 10 minus 10 is a 0 in the bottom, and that is not a possibility for our domain. We cannot allow the denominator to be 0. I mean, we've talked about that every day, I feel like, for 2 weeks now. So this, even though it says or equal to, you're not going to be able to or equal to a denominator. You're going to have to put a parenthesis there. Because if we include 10, which it says we're allowed to, but if you do, 10 minus 10 is 0, and a denominator of 0 is not tolerable. So our answer then is 4 to 10, including 4 because it says or equal to, but not including 10 because that would violate a domain rule. So there are 2 things in here that you have to be careful of. If you have a negative, you're going to have to create your own check and see if it works. And if you've got a denominator and an equal to, then you cannot bracket that. You've got to parenthesize that. You cannot include that number. Let's look at 8 minus 2x over 2x plus 7 is less than or equal to 0. This one has the same exact 2 pitfalls. Has a negative x, and it's got a denominator, and we're allowing it to equal 0. So we're going to have to soften this one. And we're going to have to do a check like we did on number 2. So I'm still going to set these equal to 0. I'm going to move the, it doesn't really matter. I'll move the 2x over. 8 equals 2x, so x is 4. It's one of my answers. And then 2x plus 7 equals 0. So let's put those on the little number line. -7 over 2 and 4. And then we're going to need to do a check here. I think I'm just going to check 0 because 0 is a pretty easy number to check. I see he falls in the middle. So I'm going to check 0. 8 minus 2 times 0 over 2 times 0 plus 7. I'm going to get 8 over 7. That's a positive number. Less than 0? No, this did not work. This is not working right here. A positive number is not less than or equal to 0. So my check did not work. That means this interval where 0 lies is not part of my answer. So my answers are going to be out here. So we've got negative infinity to -7 over 2. And I'm allowed, no, I'm not allowed to bracket that one. This one, the 4, is allowed to be bracketed because we can have a 0 for the numerator. But down here, the negative 7/2, I'm going to have to soften that one. We cannot have a 0 in the denominator. If you're looking at that orange there, that was a boo-boo. So it's 8 minus 2x, 8 minus 2x, 8 minus 2x. What are you seeing that I'm not seeing? Are you sure, Chloe? You were just wondering about that little orange dot? Okay, cool. Yeah, I put that down there at some point. Okay, so negative infinity to negative 7/2, parenthesize, always got to parenthesize the denominator, union 4 on out to infinity. Okay, let's look at number 4. Let's look at x over x plus 10 is greater than 0. Okay, in this problem, we don't have a negative x, and we don't have an or equal that's going to get us into trouble in the denominator. So number 4 is simple. Number 4 has no pitfalls, no things you got to watch out for. It's just like number 1. So we're going to set each piece equal to 0. There we've got that solved. And x equals negative 10. Greater than tells us we want to shade outsides. And they're both, neither one of them are we going to include. It doesn't say or equal to. We can't equal them. So we're using parentheses. So that tells us that these numbers won't work, like a negative 5 wouldn't work. That would give us a negative 5 over positive 5. So that's a negative number. Greater than 0? No. So this does not work. Anything 5 over 15, that's greater than 0. And anything over here, we'd get negative numbers. That cancels to give you a positive. So negative infinity to negative 10, union 0 on out to infinity. A fairly simple one there compared to what we've been doing. Number 5, x plus 14 times x minus 16 over x plus 12 is less than or equal to 0. Okay, this is the third pitfall, and this is not a new pitfall to you. 3.6a, if we had 3 different places we had to do a check, same thing here. We're going to have to do checks on these because of the way they just behave. That's a cube kind of thing. Oh, and remember the other day, I went back through and showed you with my blue marker how the 3.6a's fit a 2-dimensional system, that this is just a 1-dimensional, just on the x-axis. But I showed you how we had parabolas and stuff. I could do that with these, but it would involve vertical and horizontal asymptotes and x-intercepts and all that. And that's just more than we needed. 3.6a, what I gave you, was more than we needed. So I'm not going to show you the 2-dimensional here. But it would exist if we were to do the 5, 6 steps for these problems. Okay, so let's see what we can do here. X plus 14 equals 0, x minus 16, x plus 12. So we've got a negative 14 we've got to worry about, a 16, and a negative 12. Let's put those on our little number line. Negative 12 and a positive 16. Those are relative to each other, relative position. We're going to have to check one. Let's check 0. 0 is an easy guy to check. So 0 falls in here. So if 0 works, I know this will be shaded, and I know this next one won't be, and I know this next one will be. Remember, we alternate on, off, that kind of thing. So let's test 0. Checking 0. 0 plus 14 will give me 14. 0 minus 16 will give me minus 16. And 0 plus 12 will give me a positive. So that's a negative divided by a positive. It doesn't matter what the number is because you're comparing it to 0. So this will be a negative divided by a positive. It'll be a negative number. Negative number less than or equal to 0? Yes, all negative numbers are less than 0. So a negative whatever this is, it'd be a little more than 16, is going to be less than 0. So this checks. That means that where 0 lives works. So this segment works, and this interval works. Okay, let's see what we're going to have to do with this. This says or equal to, so your goal, your gut is to tell you to use brackets, but be careful, you can't use a bracket at 12. So let's use parentheses at 12, but these other two are in the numerator, so we can use brackets on them. So we end up with negative infinity to negative 14 bracket union parentheses 12 to, oops, what am I writing that about? 16 with a bracket. So negative infinity to negative 14, use a bracket there, union parentheses 12 to 16. All of these alternate, Ashish. You may not have noticed that, but no, yes, no, no, yes, no, yes, no, yes, yes, no, yes. They all alternate, but absolutely, absolutely with these, they'll all alternate. Negative 12. Right there, you're saying. Thank you. And good deal, Ashish. That's what you were correcting for me, Amanda? Cool. Thank you. I appreciate that. So this needs to be a negative 12 right there, all over the place. Okay, I think that's good. Let's look at our last one in this section. And same with that alternating thing, Ashish. Same with 3.6a. Whenever you're doing these with the inequalities, it always goes that way. Yes, no, yes, no. Okay, let's look at x squared plus 3x minus 18 over x squared minus 6x plus 5 is greater than 0. Okay, you can tell you're going to have to factor. So see what you can do about factoring those two. Three times 6 will give you 18, and they're 3 apart from each other. In order to get a positive 3 out of that, you need a positive 6 and a negative 3. So be sure and put them in the right spots there. Signs need to be the same, and they need to be negative. 5 times 1. Okay, so now we've got 4, and they're going to do the alternating thing also. So let's get each of our zeros. We've got them with x's, and you know they're all liars. So we're going to have a negative 6. We're going to have a positive 3. We're going to have a 5, and we're going to have a 1. So let's put that on the number line. Be careful. Dunk, dunk, dunk. Let's see. Next will come 0. Then we've got 1, 3, and 5. Okay, so relative to each other, there they are. Let's see. Because we've got more than one happening, more than two, we've got 4 things happening. We're going to have to do a test point, a checkpoint. So I'll check 0. 0 is just as good as any. You can check any number you want to, as long as it's not one of these. Don't check one that we've written down. You've got to check something that's between them. So I'm checking 0, which is right in here. And if you want to, you can use our originals. That might not be a bad idea. 0, 0, so we get a negative 18. 0, 0, we get a 5. So that's a negative number. Negative number is greater than 0? No. So where 0 lies does not work. So because you know this is not going to work, you know his next door neighbor will. You know his other next door neighbor will. You know that one won't, and you know that one will. It's crazy there because it has to go. Once you establish one of them, we know this is a no, then you know his neighbors will be yeses. Yes, no, yes, no, yes. So because we've got 4 cutoffs, we've got 5 segments to worry about. Oh, now we got to worry about, let's see, they're all going to be parentheses. because we don't have an or equal there. So negative infinity to negative 6, union 1 to 3, union 5 on out to infinity. Okay, not too tough. That's kind of a breather section, not too difficult at all. Okay, let's look at 4.1. Starting a new chapter. This is called exponential functions. It's quite different. I don't think it's more difficult, it's just different. Grab your calculator. Without a doubt, you're going to be using it somewhat. Got some things to learn. Got to learn 3 to the negative 2.7. Got to learn, we're going to look at exponential functions means you've got a variable in the exponent. Let's see, let me write that up here. Exponential means, it means you have a variable in the exponent. The exponent will be a variable. Well, that's not a variable, but we're just learning how to use our calculators right now. So let's turn it on. We want to take 3, put 3 in your calculator, and then raise it, humpy it, to the negative 2.7. Negative 2.7 equals, and we get that. And we're going to round that to 3 decimals. So rounded to 3 decimals, 0, 5, 1. Those are 3 numbers. Let's look to the 4th one telling us what to do. Let me write that down. We get decimal point 0, 5, 1, 4, 9, blah, blah, blah. Doesn't matter. The 3rd decimal is right there. They're going to tell you to round to the 3rd decimal. Look to the 4th decimal to tell you what to do. He says, never mind, not big enough. So there's our answer, 0.051. So decimal point 051. Okay, let's relate this to something you might know. Let's say it was 3 to the negative 3. Let's round it to a whole number so that you can picture this a little better. This is an experience you have had. You know that a negative exponent tells you to go to the denominator. So 1 over 3 to the 3rd. 3 to the 3rd is 27. So this 3 to the negative 3rd is about 1 over, well, is exactly 1 over 27. 1 divided by 27 gives you that, 0.037. That's pretty close to 0.051. We didn't take it quite as small as that. We only took it to the negative 2.7. So this is normal to you if you turned it into an exponent and left it as a fraction. We've done things like that, and we're going to do things like that, but we're just learning how to use your calculator right now. So just be happy that you can stick in 3 raised to the negative 2.7. That's really all you have to understand about it, and then round it to 3 places. Okay, look at another one like that. E raised to the 2.5. Okay, E is hang on a second, irrational number. It's like pi. You've got pi on your calculator. If you ask for pi, 3.141592654, and it goes on forever. It doesn't stop there. Your calculator stores it at some level. E is another number like that. E is right, second one on the left, second one down on the left, and it's in the gutter. So do second E, and you've got E raised to the, let's just raise it to the 1st power so we can see how big E is. E is that big. 2.7 is a approximation. So E is approximately 2.7. Now what does E do? E talks about nature. We use E in a formula where we describe the number of people from out of state moving to Austin over the last 25 years. That relates to E. If you want to talk about the number of trees that are dying in a certain forest in Colorado, that relates to E. What happens naturally, and you might say, well, people moving to Austin, that's not really natural. Well, yeah, it is. There are characteristics of that. If you are looking at how fast coronavirus spreads through a nursing home, that's a function of E. It's how nature takes its course. So we will use it randomly. You'll use it more in biology. Let's look at E to the 2.5. Grab E, second, and then e, and then raise it to the 2.5, and we get 12 point that. We want that also rounded to 3 places. So we're going to get 12 point, we want 3 decimal places. Let me help you there. 1, 2, 3, and then a 4, so drop it off. 182 is what we're going to keep. So 182. Now, those of you who get a little tumbleweedy, don't get tumbleweedy. Don't say that 9 turns that 4 into a 5, and that 5 turns that 2 into a 3. Don't do that. That's not legal in rounding. When you're rounding to 3 places, you look at 1, 2, 3. The 4th number tells you what to do. A 4 is too small, so you drop it off. Okay, let's start here. Number 1, let's look at f of x equals 2 to the x power. Okay, I love these. These are so cool because they always do the same thing. Just like transformations do, these will do the same. What we want to do when the exponent is the variable. Sometimes the base will be the variable, sometimes the exponent will be. But for now until spring break, like in the next hour, this will be the variable. So we are going to set up our little table like this, and we're going to put -2, -1, 0, 1, and 2 where the variable is on the x column, and that's going to happen to us till after spring break, so no worries on when is it going to look like whatever else. We're always going to use these 5 numbers. 2 raised to the -2 power. 2 raised to the -2. You know a negative exponent says go downstairs, so we get 1/4. That's 2 to the -2 is 1/4. Let them be fractions over here. That's going to make life easier for you. 2 to the -1. Again, a negative exponent tells you move him downstairs. So we get 1/2. 2 to the 0 power. Remember, anybody raised to the 0 power is a 1. 2 to the 1st power is 2. And 2 raised to the 2nd power is 4. Now, I know some of that may have been awkward, especially these negative exponents. 2 to the -2 going downstairs and squaring it. 2 to the -1 going downstairs and leaving it itself. But you will get really comfortable with this set of numbers. Let's graph that set of numbers. I forgot to get my graph out from my filing cabinet, which happens to be under my couch. So I got to go crawl under my couch. Just a sec. It's not a big couch, so it doesn't take me very long to crawl under there. Let's look at how this graphs. I just love this. This is so cool. All of our graphs will look like a variation of this. Let's see. Okay. -2, 1/4. -2, barely up. -1, 1/2, right there. 0, 1. 0, 1 is going to be our friend. Everybody's going to go through 0, 1. But you'll see that. 1, 2, and then 2, 4. 1, 2, 3, 4. Oops, that's not right. That's not 1, 2. How about 1, 2 being over 1, up 2 right there, and then over 2, 1, 2, 3, 4. Here we go. Okay, so what this guy is going to look like is that. That is f of x equals 2 to the x power. That's 2 to the x. That shape you're going to get so used to. We'll flip him around a little bit. Sometimes we'll flip him down, but 2 to the x, that's just, that's the parent function there. Now, notice that he's got an asymptote. We're not going to ever get to this x-axis. So he has got this horizontal asymptote going on. You will go out here because we can do 2 to the 10th power. We can do 2 to the 12th power. We can do 2 forever. So this line is not asymptotic, but this guy is, this arm is. So that asymptote there is one you're going to have to worry about. That's y equals 0. And you're going to have to put him into MyMathLab. Now, when you go do 2 to the x power or 3 to the x power or 4 to the x, we're going to do a couple more, and you put this in, you're not going to have any trouble doing that. That's going to be really easy to do. Pop up that palette and you're good to go. You'll see. You're good to go with that. You'll ask it to check it for you, and it'll say, nope, you're wrong, because they want the asymptote in there too. They want that one in there, and they will not give you credit for your 2 to the x, for your exponential function, without its asymptote. I don't know why they're so picky about that one and not others, but they are. So you'll need to create this, then you'll need to create the line, and you'll need to dash it. So you figure out those, that technology. I'll help you with it right now. When you go to draw this line, pull up the palette, click on the line one, and then just hit a dot there and a dot there. You just need to hit 2 dots. You know a line is made by 2 dots. So hit one place, hit another place on the y=0 line. It'll go in as a solid. Click over here where it has the little dashed to change it to a dashed line, and then ask MyMathLab to check your work. And MyMathLab will say, oh, it's fantastic. All right, I'm going to put this aside. I'm not going to erase this for right now because I want to look at another one. Let's do our number 2 problem here. Number 2 problem is going to be, oh, I numbered them differently. It doesn't matter. F of x equals 6 to the x power. I want you to see the similarities between what we're doing here and what we're doing with any base raised to the x power. Okay, so you say, okay, the x is the exponent, so I'm going to put my little series of numbers, -2 through 2, under the x column. 6 to the -2 power, that negative says go to the denominator, and we'll get 1/36. 6 squared, 6 to the 2nd power, but in the denominator. So 1/36. Then let's do 6 to the -1. The negative moves him to the denominator, and he's just himself, 1/6. And then 6 to the 0 power, remember, anybody to the 0 power, any number you've got here, any base raised to the 0 power will give you a 1. That's why this 0, 1 is going to be with us on all of these, because we're just going to be taking a base number and raising it to a 0 power. So we're always going to be going through 0, 1. Then 6 to the 1st power is just 6. And then 6 squared is 36. Okay, let me grab my old guy here and let's look at those numbers. -2, 1/36. So -2, that was a 1/4 here. Now it's a 1/36. That's way inside that. That's just almost on the x-axis. Then -1, 1/6. Again, this was 1/2 on the 2 to the x. We're hugging inside here again. 0, 1, everybody goes through 0, 1. 1, 6, so that's going to be, let me get rid of this. 1, 6 will put us there, and 2/36 is way up there. So we're going to be closer to the x-axis here. Everybody goes through 0, 1. It's like everybody goes to Atlanta when you're flying. And then we're going to steeply do that. So this is 6 to the x. Well, this one is 2 to the x. So the bigger the number, the steeper the climb. The bigger the number, the closer you are to the horizontal asymptote. So 4 to the x would be between them. 10 to the x would be really tight in here on the y-axis, that kind of thing. Okay, let's keep them moving. Our next problem, I'm going to stop numbering them because they're different from my numbering system, and that's kind of driving me crazy. Let me look at my note. I said, got to put in the graph and the asymptote. I told you that. Let's look at domain and range. Let's look at domain and range. Domain and range will be the same on all of these. So the domain of either of these. Domain is what we're using up of the x-axis. So -infinity, and this will go on up to +infinity. It's going to go endlessly that way. So the domain on all of these will be -infinity to +infinity. The range, what are we using up of the thermometer? Okay, this guy, these guys going out here. Well, let's do it a different way. What are you using up of the range? Remember, range starts at the bottom in the negative direction down here. We're not using anything up. We're not using anything up. The first thing we use up is 0, but we can't get to 0. We've got an asymptote there. So it's going to start at 0 and go on up to infinity. Be sure that you've got a parenthesis on the range there because it does not ever reach 0. This is 1 over 6. This is 1 over 36. This is 1 over 6 to the third power, 1 over 216. This is 1 over 6 to the fourth power, 1 over 6 to the fifth power. It'll never get to 0. It'll get tinier and tinier and tinier, but never to 0. As long as we're not transforming these, as long as they're just a number to a base to the x power, this is going to be the domain and range for them. Okay. Let's see. Let's look at f of x is 3 to the x power. Let's look at g of x is 3 to the x plus 4. And let's look at h of x is 3 to the x plus 4. Let's do those transformations on this. Okay, we're going to start fresh. Clean this guy off. I love this board. It's so handy. Let's first worry on our numbers. This is just a base raised to an exponent. The exponent is x, so let's put our numbers in the x column. If the exponent were y, we'd be putting our numbers in the y column. So put your -2 through 2 where under the letter that the exponent is. 3 to the -2. So 3 to the -2, the negative says go downstairs. 3 squared is 9, so we get 1/9. -1 squared, 3 to the -1 says move downstairs, and 3 to the first is just a 1/3. 3 to the 0 power is 1. Anybody raised to the 0 power is 1. There's our standard. We'll always go through 0, 1. 3 to the first power and 3 to the second power. Okay, let me graph that for you. Always going to be the same shape. -2, 1/9. -1, 1/3. 0, 1. Everybody goes through there. 1, 3, and 2, 9. So our basic guy here is doing something like that. And if they're asking you to graph it, you're going to have to show the asymptote. All right. Let's look at 3 to the x plus 4. Let's not do the math. Let's do what you know about transformations. This is a transformation on the x. It's attached to the x as opposed to this one over here that is away from the x function. So you know that this is a horizontal shift. You know that we're going to be shifting, and this is also always going to be there. It's the opposite. 4 to the left here in order to do this. And then on the x function, on the horizontal function, we're going to go in the opposite direction. So each one of these points is going to move 4 to the left. There's a guy, 1, 2, 3, 4. Here's a guy, 1, 2, 3, 4. Here's this little guy, 1, 2, 3, 4. This one, 1, 2, 3, 4. This one, 1, 2, 3, 4. So like that. Ought to be prettier and curvier, but you get the idea. So this is 3 to the x plus 4 of a transformation on the x because it's up there with the exponent and it always lies. So we're just going to shift it to the left 4. You'll do that as a horizontal shift, and then you'll take that slider at MyMathLab and move it to -4. Still has the same asymptote, still has the same domain. Domain will be all of the x-axis. Range, this red one didn't start any sooner than the black one, so it'll start at 0 and go on up to infinity. Same domain and range as the previous. Okay, let's do our last one here. H of x equals 3 to the x, starting with the basic graph, and then we're transforming it plus 4. This is away from the x function, so you know that that's going to be a vertical shift. So we're talking about a vertical shift here, and sure enough, 4 up. That's a vertical shift. So let's take our original 3 to the x, that's the black graph here, and we're going to move every one of these points up 4. So this guy will go 1, 2, 3, 4 right to there. This guy 1, 2, 3, 4 right to there. This one 1, 2, 3, 4. This guy, same thing. And this guy. So something like that. This blue one right here is 3 to the x plus 4. Domain on him, same old, negative infinity to positive infinity. It's going that way, it's going that way. It's still using up the same, all of the x-axis. Range will be a little bit different because he doesn't get down in this area like the black and the red one do. The blue one, the range starts, nope, blue is not using up the y-axis, nope. Doesn't use it up till right there. Let me put the horizontal asymptote. And that is y equals 1, 2, 3, 4. He moves up 4 also. So the range will be from 4 on up to infinity. He doesn't ever, this blue exponential function doesn't ever get to the asymptote, doesn't ever get to the y equals line. So that'll be a parenthesis on the 4. Okay, so we have a new shape. We're just going to shift him around the same old way. We won't spend a lot of time on this. 4.1, it does not bleed over into the others. Don't, that's okay, we're changing. Okay, let's see what we're doing next. Let's see, domain and range, we did that. Okay, let's look at some other shifts. Let's look at the reflections across the x-axis and the reflections across the y-axis. How are you going to recognize those? So f of x equals 5 to the x. And then we'll look at g of x equals negative 5 to the x. And then h of x equals 5 to the negative x. Okay, let's first look at 5 to the x power. Again, the exponent is where you're going to put your numbers. It's an x, so put your numbers in the x column. And then 5 to the negative 2. And I know some of you are like, I don't know what to do now. And others of you are, you got the column done. It's like anything else. It occurs to some of us more quickly than others. So 5 to the negative 2. The negative tells you to go downstairs, and then you'll be doing 5 squared. So we're going to get 1 over 25 there. 5 to the negative 1, the negative tells you to go downstairs, so we get a 1/5. 5 to the 0, 5 to the first, 5 to the second. Notice everybody uses 0, 1. Okay, let's do negative 2, 1/25. Oh my gosh, that's really going to have to hug it. Negative 1, 1/5, 0, 1, 1, 5, and then 2 is off the charts there. I don't know if they're going to ask you for the horizontal asymptote, but if they do, it's right there. And I can promise you, it is very frustrating to do MyMathLab, know you've got this drawn correctly, and then have it say, no, it's wrong. That's very frustrating. Okay, let us at the other two. When we've got a negative 5 in front, hang on a second, let me organize my stuff here. Pen. Okay, let's look at g of x equals -5 to the x power in front. So let's do the same thing. We've got x there, -2, -1, 0, 1, and 2. And then we are going to say 5 to the -2. Remember, this negative just waits on you. 5 to the -2 we already know is a 1/25. Put a negative in front of it. 5 to the -1 you know is 1/5. Put a negative in front of it. 5 to the 0 power is 1. Put a negative in front of it. Going to go to 0, -1 there. 5 to the first power is 5. We need a negative in front of it. So we're just taking these same numbers and putting a negative in front of what we got. Okay, let's look at what that looks like. -2, -1/25. -1, -1/5. 0, -1. 1, -5, and 2, -25 won't be on here. So we've got this happening here. So what happened here is this is reflected across the x-axis. So when you have a negative in front here, this is going to reflect across the x-axis. Okay, the negative in front will reflect it down, reflect it across the x-axis. You just mark reflect across the x-axis when it's got a negative in front of the base. Okay, let's look at h of x where the negative is up here. Let's see what happens there. Again, we've got an x there. So string those numbers there. And then let's see, we've got a 5 to the negative of a -2. So if we put a -2 in for x, that negative will change it. So this is saying 5 to the second power. So that'll be a 25. If you put a -1 in here, the negative of a -1, that's a +1, 5 to the first power will be a 5. 0, there is no such thing as -0, so it's just 5 to the 0 power, so it's still 1. And then put a 1 in here, 5 to the -1 power. 5 to the -1 says go downstairs, and then this will be 1/25. So let's graph those and see what happens when we put a negative on the x. Let's see. So we've got a -2. Try to straighten this out so it doesn't drive you nuts. -2, +25. So -2 way up here. I'm off the scale. -1, +5. 0, 1. 1, 1/5. And 2, 1/25. So something like that. So this green one here is -x, the negative on the exponent itself. This one is definitely the reflection across the y-axis. When you've got a negative for the x there, let me write that in here. This, wrong pen. This will reflect it across the y-axis. So when it's got a negative on the exponent, you're going to be reflecting it across the y-axis. When it's got a negative on the number itself, the base itself, that's going to reflect it across the x-axis. Probably memorizing that is most helpful. You can generate your own tables, whatever works for you. We're sort of run out of characteristics that we're going to be looking at. So this might be a limited amount, limited enough that you can memorize that. You decide. Let's see. So it would be symmetric about the x and the y-axis. One is symmetric, yeah. This one is symmetric about the y-axis. This one's symmetric about the x-axis, but not both at the same time. You see that, Chloe? Cool. Okay, let's put that up. Let's move forward with a little more mathy stuff. Let me cork my pens so they don't go dry. That's not the right pen. I have two sets of pens. It's fine if I write with these pens on my paper, but it is not good to write with a Sharpie on a whiteboard. That is not a happy situation. I know how to fix it though, and that's good. Okay, let's look at our next one. We are going to spend a little bit of time in consumer math now. So let's look at our consumer math problems. We've got some interest problems going here. 1 plus, you will not have to memorize these formulas. Okay, we are going to look at if you have $30,000 to invest, $30,000 to invest, you're going to invest it for 5 years, and your interest rate is 5.5%. We're going to see how much money you're going to make if you put it in a fund that turns over your interest semi-annually, that compounds your interest semi-annually, that compounds your interest several other ways. So the first way we're looking at is what happens to this money if we compound it semi-annually. Okay, A stands for accumulated funds. How much money are you going to have at the end? P stands for principal. That's the money we're putting into the account. 1 stands for 1. Plus stands for plus. R stands for rate, but we can't use it as a percent. You've got to use it as a decimal. So move the decimal point over 2 places. Boom, boom. So we get 055. So we'll use 0.055 right there over n. N is the number of times. N starts with number. Number starts with n. The number of times it's being compounded. Semi-annually tells you it's being compounded twice. Semi means twice. You know that. Close the parenthesis. Raise it to the n. N is still 2 times time. How many years is this going to be in the account? 5. So I'm going to change this right now. 2 times 5 I know is 10. I just want to be sure I know it's 10. Grab your calculator. Everything's going to be done left to right on your calculator. You know what? I'm not comfortable enough doing that. I'm going to do the last thing last. I'm going to do these parentheses. So 1 plus 0.055 divided by 2. Your calculator knows it doesn't mean all of that because it's 2 terms. You didn't put it in parentheses. So it knows you mean only the 055s getting divided by 2. Let's equal that. Let's find out a value for that. And then let's raise it to the 10th power. Humpy 10 equals, we get 1.3. And now back up and multiply it times 30,000. Times 30, boom, boom, boom. And we're getting 39349. It's money, so make it look like money. So you're getting $39,349.53 after how long? After 5 years. We're going to do this many more times. Let's do this again. Let's say that you have found an account that will compound your interest quarterly. So A equals principal is still 30,000. That's the money we're putting into the account. 1 plus interest rate is still 5.5%. Divided by how often is this being compounded? Quarterly. So 4 times a year, quarters. Close it. Raise it to the n times t. 4 times the time is 5. That's 20. That's what I'm going to raise it to. Let's do the same thing. Let's start on the parentheses. So 1 plus, let's see, that's kind of got a glare there. Let me do it over here so it's not quite as glary. 1 plus 0.055 divided by 4 equals, then we're going to raise it to the 20th power, humpy 20, and then times 30,000. and we're getting a new number, $39,421.99. Oh, that 5 tells us round it up. So $39,422.00 rounded to the nearest penny. So let's see, when it was quarterly, we made a little bit more money, 39,000 both of them, but you know, like $60, $70 more, not a whole lot more. Let's next look at monthly. We're going to take our same $30,000, still at 0.55 rate. We're going to compound it. We found an account that'll compound it 12 times a year. We're going to raise that to the 12 times 5 years. That's 60. We're going to raise it to the 60th power. So let's do that. 1 plus 0.055 divided by 12 equals, raised to the 60th equals, times 30,000. And we're getting $39,471.11 rounded to the nearest penny. So we made a little bit more money now, $50 more almost over the quarterly. And then finally, we're looking at what's called continuously compounded. Continuously compounded. That is not this formula. Now we're going to use this formula. A equals PERT, although it's not. A equals P times E raised to the RT. But my classes that have to memorize this, I just tell them it's PERT. So let's see, we got A equals P is our principal, that's $30,000. Now continuously, you know, you're thinking, what does that mean continuously? Because if I'm doing it every second, that's not often enough. It needs to be done, no, not every half second. It needs to be, if it's being done continuously, it has to be done more than that. It's a formula, it's what it's called, we'll live with it. Times E, remember E is that funny thing that happens in nature, raised to the rate. Let's see, the rate is 0.055 times the time times 5 years. Okay, we can go straight through on this. 30,000, move it over, sorry about that again. 30,000, this is not working out well. I want to show you both. You're just going to have to trust me. 30,000. There we go, that's a little better. Times E, and we want E right here. So do second E, and then it's already raised to the, see, it's already got the humpy key there for you. And then put in parenthesis, it's already got it, 0.055 times 5, and close the parenthesis if you feel like it, but you don't have to. Hit the equals button. And there we go. There's our value, $39,495.92. That's the greatest of the values. That's the most money you can make. The more often that the interest is thrown back into the account. Here, only twice a year is it thrown into the account. Here, 4 times a year. Here, 12 times a year the interest you've earned has been thrown back into the account to gain more interest. Here, it's happening continuously. So if you're doing continuous, you have to use this formula. If you're doing a specific number, you'll always use the general formula for interest. You won't have to memorize those formulas. They'll be on any test. Okay, let us look at inflation. Here's a formula for you. S equals C times 1 plus R raised to the T. That models inflation. Where C is the current value, we're going to do a home. We're going to look at how much a home raises in value. So C is the current value of your home. R is the inflation rate. It's going to be the percent of inflation. So R is the inflation rate, and you'll have to turn it into a decimal point, of course. S is the inflated value, how much it's worth now. or how much it will be, sorry, how much it will be worth now if we continue to inflate at a certain rate, and T is the number of years that this is going to be happening. So let us say that you have a $75,000 home, and we want to know what it's going to be worth 26 years from now. And we are going to assume an 8% inflation rate per year, which is crazy. We're not inflating at that level anymore. We did a while back. So our inflated value, what our house is going to be worth, will be equal to C, our current value of our house, times 1 plus the rate that we're looking at here is 0.08, which is crazy. It's not happening. Raised to how many years? 26 years from now. So let's put that in our calculator. 75, I just prefer to do this end first. 1 plus 0.08, and I get that you can do that in your head, 1.08, raised to the 26th power, humpy 26, and then times 75,000. But before you do that, look at what we're about to multiply 75,000 times. 7. That means the value of your home is going to be multiplied times 7 times the 75,000, and your home will be worth that amount of money. So your future value is going to be $554,726. They ask you to round to the nearest dollar. So 554, $500,000, more than $500,000. Your $75,000 house. Dang, I know. But 8% is just not happening right now. And you know there are variables. You know if you let your house look like crap, that's not going to happen, etc. Okay, we got 9 minutes for one more problem. Let's look at our one more problem. I think I'm going to start on a fresh sheet of paper. I don't know what the inflation rate is right now. Does anybody know annual inflation rate? It's not 8% though. Okay, there's an old-fashioned formula, x plus 35, no exponents involved. So this is called a linear formula. This is a linear model because that's a line, y equals mx plus b. That's a line. So this is a linear model of something that we're going to be talking about. And here is the exponential model. It's going to have an exponent in it. Let's see, 32.1 times e raised to the 0.0223x. Okay, so that little bitty number here, that exponent is 0.0223x. That's the exponent. So we have two models for the same thing. What are we talking about in this one? These both are different ways of representing, let's see, these represent the percent, thank you, little fast Google in there. So 2 times would make your house worth a whole lot less if we used 2% there. Let's do that real fast. Let's see, so your house is worth $75,000, 26 years from now. 1 point, and Charles offered 2.224, 224, yeah, of course, that's what it equals, raised to the 26th power. So we're only going to multiply it times 1 and some, 1 and a little bit, times your $75,000 house equals, now it's worth 133, 150 would be double, so $133,000, almost doubles in the span of 26 years. Other things other than inflation affect home values. You know, the DFW area now is crazy high with house prices going up in the last 20 years or so. So lots of things affect that. Okay, these two models, different models, you know, you can have different ways of representing something. These are both representing the percent of seniors, like seniors in high school, who applied to more than 3 colleges X years after 1980. Okay, so these two different ways of representing, they're both going to be close. One might be closer than the other, and that's kind of going to be your job, which one is closer. These represent the percent of seniors, so we're going to get a percent answer for each one, who applied to more than 3 colleges X years after 1980. So we're going to have to be subtracting 1980 for our X value for there and for there. Okay, A asks you to determine the percent with the linear model. Determine the percent using the linear model for 2010. Okay, so if we're going to use the linear model, we have to use f of x equals x plus 35. Okay, let's figure out what x is. X is the years after 1980. So how many years after 1980 is 2010? Just subtract them and you'll get 30. So x equals 30. 2010 is 30 years after 1980. So f of 30, if you want to be particular, 30 plus 35, so we're getting 65% of seniors based on this model. I don't know what the truth is, but this model that somebody has said will get us close adds 35 to the year. So we're getting 65% of seniors. Using the linear model, it tells us 65%. Okay? B is asking us to do the same thing. Determine the percent of seniors using the exponential model for 2010. Same exact information, we're just going to use our other model. So g of x equals 32.1 times e raised to the 0.0223 times x. X again is just the number of years after 1980, so it's still 30. So I'm going to put a 30 in there. Grab your calculator. 32.1. I'll clear that. 32.1 times e. Go grab e using second function raised to the 0.0223 times 30. Close the parenthesis if you're in the mood, if you're anal retentive, equals 62.668. So 63, let's round that to 63%. So we got very close there to one to the other. The two models model very closely. They should, because they're supposed to be telling the truth. One is doing it with a linear model, one is doing it with an exponential model. And then C is going to ask you which model fits the bar graph better. Which model, linear or exponential, which model fits the graph better? Okay, that you'll have to look at MyMathLab for. That MyMathLab has a graph. You know, let's just say that 2010 was 59%. So this is the truth. This is the real life, and they're asking you which of these modeled it better. Well, 59 is real. This one got closest. This one's a little further off. So your answer would be the exponential model. If, however, let's say that for 2010 it were 66%, then which one is modeling it better? 65% is closer, and that was the linear model. So your answer would be linear. So you will look at what the bar graph tells you and see which of those got closer. Okay, we are good to go. We are starting spring break, or at least if you have no other classes, you are. We're done with 4.1 exponential functions. This afternoon I will open up all of MyMathLab so that you can get in there. The half of you that isn't perfect, the rest of you take a break. Get caught up on these sometime in the next week before we come back on the 22nd. You don't want to be lagging behind. I would not do 4.1 right now. I would maybe do 4.1 next weekend, or do 2 of the problems a day. You know, you don't want to get too far ahead. You don't want to, you don't want to be done with it 10 days before we meet again. The most important problems, let me look at exactly what 4.2 is doing. No, do them tonight if you want. There's almost nothing that you don't have to worry about forgetting. We're starting fresh stuff in 4.2 that is almost not related to 4.1. So do it, fix it when you want to fix it, and you won't have any troubles. Questions? Okay, I'm going to stop recording.